Okay, so in this lesson we're looking at some typical questions for the dynamics part of A-level mechanics. So dynamics is everything to do with force and motion considered together. So typically that is Newton's laws, looking at momentum and looking at work and energy. So this is a deceptively simple question. It shows a particle represented by the circle. It collides with a wall. We're told the collision is elastic, and we're asked to say which of the four diagrams shows the correct change in momentum that occurs during the collision. And if we sort of thought to ourselves, right, okay, let me think about what that might look like. So think of it like a ball that comes along here. It bounces off the wall, comes back in this direction, ends up here. And which of these diagrams looks most like this? And it's this sort of way of considering it which draws towards this answer C. But we need to think about what exactly it is we're being asked to work out. So we're being asked to work out the change in momentum. So that's going to be our final momentum minus our initial momentum. So if the final momentum is an arrow in this direction, and the initial momentum is an arrow in this direction, what I have is I've got that vector minus that vector. So next we can say to ourselves, what does it mean to say that we've got minus a vector? Well, what that means is that is the same as saying this vector plus and a vector going in the opposite direction. So once we've worked this out, it now becomes very much easier to see which of the answers. So it can't be A, because in this case we're shown with the initial momentum vector still in the same direction. Here again in C we're shown with this initial vector in the same direction. And by the way, if we think about this, what they're doing here is they're doing a calculation of the final momentum plus the initial momentum. Okay, so this one is the initial momentum plus minus the final momentum. So that would be the initial minus the final, this one. In here, what we've got, well, we have the final again plus the initial. So we've got the final plus the initial. So the only one that can possibly be the correct answer is this one, where we have this is our final momentum and this is minus our initial momentum. So the answer is B. Right, question 2. So again, we're showing this diagram. Given this option of one of these four rather complicated looking expressions for the answer. And what we're looking for in the answer is the speed of recall of the daughter nucleus. So here we've got the parent nucleus, and it undergoes some sort of radioactive decay, and it emits an alpha particle, and the daughter nucleus is what's left, and we're looking for the speed of this part. Now this is a question about conservation of momentum, so the total momentum beforehand is equal to 0, which means the total momentum, the final momentum, is also equal to 0. So what can we say about the momentum afterwards? Well, we have the momentum of the daughter molecule and the momentum of the daughter nucleus, I should say, and the momentum of the alpha particle. So the alpha particle, it has a mass v and velocity, some sort of velocity v. And we have the daughter nucleus, it has a mass. Well, what's the mass of this one? It's going to be m minus the alpha particle's mass, and then its velocity, I'll call that v dash. Okay, So that we know from these two added together, plus this momentum is going to be m minus m times v1, and the minus sign putting in there because these are in opposite directions and momentum is a vector. So that means that we can say that v dash is equal to v all over, so the sign goes out because it brought across to the other side, that's all equal to 0. So we've got the velocity of the daughter molecule is equal to the mass of the alpha particle times its velocity, its momentum, divided by m minus m. Okay, we then need to know what the velocity is of the alpha particle. We're told its kinetic energy, which is equal to half mv squared, is equal to E. So that gives us that the velocity of the alpha particle is equal to the square root of 2 times E divided by m. So that gives us then that we have the velocity is equal to m times the square root of 2e over the square over m, all over m minus m. And that will give us, if I have m times 1 over the square root of m, that equals the square root of m. So that would give me that the velocity is equal to square root of 2me m. So my answer is A. Now, you'll notice that once I'd got to this stage, in actual fact, I should already have seen that the answer was A without having to do the second part. So we could have taken a shortcut with this question. What you could do in an exam in this sort of situation where you notice, yeah, it's going to be that one. To save time, you say, yeah, okay, I'll take that one. And then when you have time left over at the end of the exam, when you're checking questions, you could go back and do this last part just to double check that it's correct. Okay, right, question 3. So here we have, again, a conservation of momentum question. Trolley 1 has mass 2 kilograms. It collides on a horizontal surface with trolley 2, also of mass 2 kilograms. The collision is elastic. Before the collision, T1 was moving at 4 meters per second and T2 was at rest. So we've got an elastic collision. The masses are 2 kilograms and that was the initial velocity. So my mass of one is 2 kilograms. Mass of the second one is 2 kilograms. Velocity before here was equal to 1 before was equal to 4 meters per second. The velocity before for trolley 2 was 0. So we can get the momentum. So the total momentum before is equal to m times v. So that's 2 multiplied by 4. Plus 2 multiplied by 0, so that's equal to 8 kilograms meters per second. And we know that the means that the momentum after is equal to the momentum before, therefore the momentum afterwards has to be equal to, the total momentum afterwards has to be equal to, also equal to 8 kilograms meters per second minus 1. So we can see which of these is likely to be the correct answer. So, what are the options? Well, by the way, let's not forget, and I didn't write this in here, which I should have done, is the direction of that momentum is in this direction. So the total momentum in that direction, so the total momentum afterwards is 8 kilograms meters per second in that direction. Okay, so they say after the collision, one option is T1 is at rest and T2 moves at 4 meters per second. So what would that give us? That would give us the momentum afterwards is equal to 2 times 0 plus 2 times 4, or otherwise 8 kilograms meters per second minus 1. And the direction will be in this direction. So that one's possible. This one says T1 will rebound from T2 at 4 meters per second. It doesn't actually tell us what happens to T2. We could make the assumption 0, but even in that case, we would get an answer of for 2 times minus 4, because it's in the opposite direction, plus 2 times 0 to give us a momentum afterwards of 8 kilograms meter to the second one, because it's in the opposite direction. So this one is not possible. T1 and T2 both moving at 2 meters per second. Well, if that happens, what we have is we have effectively 4 multiplied by 2.8. We would have a momentum of 11.2 kilograms meters seconds minus 1 in the correct direction, but the wrong magnitude. And then finally, the last one, we've got the momentum afterwards is 1.4 times 4, which is 5.6 kilograms meters seconds minus 1. So the answer is A. Again, the shortcut for this question is that they told us the elastic is collision. So if one object is moving, the other object is at rest. The collision is elastic. It means the first object starts, the second object moves away with the same velocity. Okay, moving on to the next question. Okay, apologies for that, slightly knocked the camera stand. So question 4, lift and its passengers have a total mass of 500 kilograms. We're told they're accelerating upwards and the acceleration is equal to 2 meters per second squared. We're told that G is equal to 10 meters per second squared, and we're asked to work out what the tension is in the cable. So this is a question to do with Newton's law, specifically Newton's second law. Whenever we say we've got mass and acceleration and we're interested in force, we're going to use Newton's second law, which is force equals mass times acceleration. That means the force in this case that is causing that upwards acceleration is equal to 500 multiplied by 2, so the force equal to 1,000 newtons. Now, they've put in an answer of 1,000 newtons. Very easy in this question to then go, okay, that's my 1,000 newtons, pick this as the answer. But remember, we're not asked for the overall force on the lift, we're asked for the tension in the cable. So if we do a quick free body diagram, think about what are the forces acting on this lift. We have, yes, the tension upwards, but there is a force downwards of the weight, and we know that it's accelerating upwards, so the tension must be larger than this force, so that overall we have a resultant force. So we can say that the force on the lift is equal to the tension in the cable minus the weight of the lift. What's the weight of the lift? Well, weight is equal to mass times acceleration due to gravity. So that means the weight is equal to 500 multiplied by 10, which gives us the weight is 5,000 newtons. So coming back here, we've got the tension is equal to the force plus the weight, the resultant force plus the weight, so that equals 1,000 plus 5,000 gives me the tension is equal to 6,000 newtons. So the answer for this one is D. Right, question 5. These come up quite regularly in multiple choice questions, this sort of thing where you have to consider various parameters, what's happening, whether there is a change, and which ones are being shown to change correctly. So in this case, we're mostly interested in momentum and kinetic energy here. Total energy, well, we know that it is a principle of physics that total energy is always conserved. So automatically that tells us that the answer to this cannot be B. So we can immediately eliminate B. We don't have to consider it any further. So we're then looking at what type of a collision is this? This is an elastic collision. Well, in an elastic collision, we have momentum. Yes, it's always conserved. So it's going to be one of these three answers, but it can't be B. So we've already eliminated A. We've eliminated B. So it's going to be either C or D. It's an elastic collision. An elastic collision means that kinetic energy is conserved. So the answer here is D. Now the next question, it's looking at really at establishing our understanding of how expressions or equations relate to the graphical representation of the function. So we're looking at graphs of kinetic energy and momentum against time. We're told that an object is accelerated from rest by a constant force for a time t, which graph represent the variation of time with a change in kinetic energy and change in momentum. So if we think about what this means in terms of what sort of graph relationship we would need. So if we look at momentum first of all, so we have that impulse or force times time is equal to the change in momentum. I've got momentum on the y-axis, so I'm just going to rewrite that equals F times t. This is my y term, this is my x term. We're told this is constant, so that's m. So this is saying that change in momentum is directly proportional to t. Now turn attention to the kinetic energy. We have that the expression we know for kinetic energy is equal to half mv squared. V is not constant, V is changing with time. We're going to have some sort of function. So we can say that the velocity is going to change. And how do we get this change in velocity? Well, we've been told force, and we know that force is equal to mass times acceleration, which gives me acceleration is equal to force over mass. And I also know that acceleration is the change in velocity over time. That gives me equal to, that is equal to that. So that gives me that the change in velocity is a times the change in time. And putting in that expression from above, that gives me F m delta t. So for my kinetic energy, what I'm expecting is an expression that looks like this. So it gives me Ek is equal to a half s squared over mp squared. So what does that mean? It means kinetic energy is proportional to the time squared. Right, so in terms of the graph, what we expect is we expect a linear function for the momentum, showing direct proportionality. So that gives us, it's either A, can't be this one, or C, it can't be this one. And we know that the kinetic energy has a squared function, so it could be this one, but it can't be this one, which means the answer has to be A. So the answer to that question was A. Next one, which one of the following could not be used as unit force? So this question is looking at equations that have force in the equation and using those equations to determine units that we could use for force. So if we look at this first one, we've got amps, we've got meters for length, we've got this unit T, which is the unit Tesla, used for measuring magnetic fields. So this equation is force equals magnetic field strength times, or magnetic flux density times the current times the length of the wire used on the force on a current carrying wire in a magnetic field. So in terms of unit, that gives me 1 unit of force is the same as if I had, let's put a value of 1 for each of these. I had 1 Tesla multiplied by 1 amp multiplied by 1 meter. So that gives me 1 Newton is the same as saying 1 amp Tesla meter. So that one, yes, can be used for force. I'm just going to skip this one out. So we've got this one. Here we've got something that looks very similar to momentum. So I think this is this equation that we're looking at here. So that gives me 1 Newton times 1 second is equal to, if I have when 1 kilogram meters seconds minus 1. So dividing both sides by seconds, that gives me 1 kilogram meters seconds minus 2. That one also can be used for force. Here we've got joules, the unit for work done or energy, and again distance. So this is likely to be work done is equal to force times distance. So that gives me 1 joule is equal to 1 Newton times 1 meter. So that gives me 1 Newton is equal to 1 joule e to the minus 1. So that one's fine. So by a process of elimination, it tells me the answer must be this one. Now, this one, it's saying here we have power and time. So how this relates is we have, once again, work done is equal to force times distance. We have that power is equal to work done over time. So that means that power times time equals force times distance. So that would give me that 1 watt times 1 second is equal to 1 Newton times 1 meter. To give me 1 Newton is equal to 1 watt second to the minus 1 meters to the minus 1. So this one is wrong, and that's what they want. They want the value or the units for force that could not be used for force in this case. Okay, so question 8. This is a question about conservation of momentum in explosions. There's no quantities here. It's always useful, or as in most cases, it's often useful, I should say, to start with the diagram. So what we've got is, before we have the nucleus of a radioactive isotope, so shown with a circle with an X in it, and it's just sitting at rest, so it's not doing anything. Doesn't seem terribly interesting. We can say that the total momentum before is 0. Then we have, afterwards, it emits an alpha particle. So if it emits an alpha particle, there has to be movement of that particle. So it's moving away with a particular velocity. And we also have a new nuclide produced, which is labeled as Y. So that has to be moving in the opposite direction. Why? Because the momentum, the overall momentum, has to equal 0 for conservation of momentum. Okay, so which of these is going to be the case? Well, the first one says the momentum of Y, which is this term, is equal and opposite to the momentum of the alpha particle. That has to be true if we're going to have 0 momentum overall. So this one looks to be correct. The momentum of Y is equal to the momentum of X. Well, that's not necessarily the case. Well, in fact, I should say that's definitely not the case, because remember, the momentum of X is 0. This is not 0. So this is definitely false. The kinetic energy of Y is equal to the kinetic energy of the alpha particle. So in this case, this is an explosion. The overall kinetic energy is not conserved. And the Y particle will have a different speed to the alpha particle. It will also have a different mass. So we can say that this one is false. And I'll come back to this one and we'll look at how we could show that maybe to ourselves if we wanted a bit more convincing. And then the last one, the total kinetic energy is the same before and after. That's only in elastic collision, so this one is definitely false. So the answer for number 8 is A. So I said for part C, you could convince yourself a little bit more calculation that this is correct, a little bit more manipulation of the equation. So let's do that. So we've said that after the explosion, the total momentum is 0. So we have that the momentum of the Y nucleus is equal to the momentum of the alpha particle. So I've used V dash and V for their respective speeds. And so I can get an expression for the speed of the Y nucleus in terms of the alpha particle speed. So that's going to be masses of the alpha, so the mass of the alpha particle times its speed divided by the mass of the nucleus. Okay, so the kinetic energy is equal to half mv squared. So the kinetic energy of the Y nucleus and the kinetic energy of the alpha particle, just like that. We can substitute for our speed here, so that gives me a half times the mass of the nucleus divided by the ratio of the masses times 1b squared times v squared, and that gives me E. Okay, is equal to a half. I've got the square at the bottom, so we're going to have the alpha particle's mass squared divided by the mass of the Y nucleus times the velocity squared. So clearly this is not equal to this. This is equal to mass of the alpha particle divided by the mass times a half. So its kinetic energy is different by the ratio of the masses. So definitely C is incorrect. Okay, question 9. So I'm going to start by having a little sketch for myself. So before, what I have is I have the car. It's moving some speed. It's got a mass of 580 kilograms. And it collides with a van. Its mass is 1200 kilograms and its initial velocity is 0. So that's before, and then after we have the car has recoiled and its velocity is now 1.6 second, and the van is moving in this direction at 6.2 meters per second. Okay, and we're asked what is the initial velocity of the car. So we're looking at conservation of momentum. So before, what have we got? The total momentum before is equal to 580 multiplied by the velocity of the car plus, well, it's 1200 times 0. So my momentum before is 580 times velocity of the car. Afterwards, the velocity afterwards, I'll pick this direction as the positive direction. So I've got 580 multiplied by minus 1.6 plus 1200 multiplied by 6.2, and put those into the calculator, which gives me total momentum afterwards is equal to 6,512 kilograms meters per second. From conservation of momentum, you can say that momentum before is equal to the momentum afterwards. So that gives us the momentum before, which is 580 times velocity, is equal to 6,512. So that gives me the velocity is 11.23 meters seconds to the minus 1. So question 9, which of these is the answer? The answer is B. Question 10 is a question to do with this quantity called impulse. We have the mass of the car is 500 kilograms. It's traveling at 10 meters per second. It hits a wall and it says the front 0.3 meters of the car crumples as the car is brought to rest. So the distance traveled is 0.3 meters. What is the average force on the car during the impact? So we've got something that will allow us to work out momentum. We're looking for to work out force. So in terms of relating force to motion, there's always two ways we can think of this. It's either going to be force equals mass times acceleration, or force times time equals the change in momentum. We're going to use one of these approaches. Either would be fine in this question. The issue we have is we either have to have some way of working out the acceleration, or if we use this approach, we need to have some way of working out the time. So the first part of this question, doing this question, is essentially a SUVAT question. So we've got SUVAT. I'm going to assume that the acceleration is constant, so I can use SUVAT because it asks me for average force. So it does not ask me what is the peak force that the car undergoes as the front of the car crumples. So because it's looking for average force, I can use the assumption that the deceleration is constant. So distance 0.3 meters, the initial velocity was 10 meters per second, final velocity is 0, looking for acceleration, don't worry about that one. So which of the SUVAT equations will give me this one? Well, that is v squared is equal to u squared plus 2as. So that gives me that a is equal to e squared minus u squared divided by 2 times the distance. So a is equal to minus, which is what we expect because it's deceleration, 10 squared divided by 2 times 0.3, which gives us an acceleration is equal to minus 167 meters second minus 2. Then we've got force is equal to mass times acceleration. So that gives me the force is equal to mass 500 multiplied by minus 167. So that gives me the force is equal to minus 83333 newtons. So which of these is going to be the one we take? Well, it's clearly D. Okay, so next question. We're told the rocket has a mass of 1200 kilograms accelerating upwards at a certain amount of acceleration. What is the thrust? So we're looking for the force. So we're looking at, again, using Newton's law relating force to acceleration. Useful as always, do a little diagram. Think about what I'm saying. I'm saying that there is a force upwards, the thrust. I'll show that with a capital T. And I need to think about, is there any other force acting on this? Well, clearly there is. There would be the weight downwards. And we're told that overall there is a certain level of acceleration, 1.4 meters per second squared. So that gives me the resultant force is equal to the thrust minus the weight. We're looking for the thrust, that would be equal to the force plus the weight. So I need to calculate those two things. Well, first of all, for the resultant force, that's equal to mass times acceleration. So that's 12,000 multiplied by 1.4. So that gives me that the resultant force is 16,800 newtons. And the weight is equal to m times g. So the weight is equal to 12,000 times 9.81. 12,000 times 9.81 gives me an overall force of 117,720. And I just simply need to add those two together to get the thrust. So the thrust force is equal to force times weight. That's equal to 134,520 newtons. Which one of these is the closest answer? It's 1, 2, 3, 4, 5. It's going to be this one. So the answer is C. Okay, so question 12. The graph shows how the resultant force F on a football, which is initially at rest, varies with time. Which graph shows how the momentum P of the football varies with time? So the thing we're looking at here is we have this expression for the change in momentum which is the change in momentum, is equal to force times time. So another way of understanding that is to say the change in momentum is the area under the force time graph. So what we expect is we expect to see that the momentum is going to increase as the area under the curve increases. So initially we're going to have a very small area, again made a bit bigger but still very small, eventually becoming a large area and then increasing as we go on. Now the way to think of this is that each of these trapeziums, they start off small, they get very large, so I'm going to have a small increase in the momentum here. This becomes a large increase in the momentum over this, and these are roughly the same, and then it goes back to be a small increase in the momentum at the end. So which of these graphs shows us the momentum starting with a small increase, the increase becoming larger, and then the increase becoming smaller again? When we talk about increase of a variable on the y-axis of a graph, we're talking about the gradient of the graph. A small increase means that the gradient is low, the graph is fairly flat. Large increase, a high gradient, means that the graph is steep. So for this first one, A, what we see is we see an increase in the momentum, but it's always constant. And then we see a decrease in the momentum. Well, this can't happen. So this definitely isn't the case. Here we see constant increase at the start. Yes, becoming smaller, but just then staying constant again. So it's not this one. Here again, we see a constant increase in the momentum. We then see the increase becoming smaller. So that matches this second part, but this doesn't work because this is showing a constant increase. So that's wrong. So this one, where it shows a small increase at the start, then a large increase in the momentum in the middle, and then again a small increase at the end, which corresponds to what we see in terms of the change of the area under the graph. So the answer for this one is D. Right, again, question 13, another one of these unit questions. We're looking at expressions for an equation. So this time we're looking at power. So power is equal to work done over time. We can see also that here we've introduced this first one, Newton. So here we've got force. We know that work done is equal to force times distance, which means that power is force times distance over time. Means that power is equal to force times speed. So for the first one, what can we say? We can say, using this equation, 1 watt is the same as having 1 Newton multiplied by 1 meter per second to give us 1 watt is equal to 1 Newton meters seconds to the minus 1. So this one is fine. This one here, we've got for C, we've got 1 watt is equal to 1 joule times 1 second to the minus 1. So that gives us 1 watt is equal to 1 joule seconds to the minus 1. Well, is this correct? Well, this is what we expect from this expression. 1 joule divided by, work done in joules divided by time in seconds. So that one's fine. And then we have units of power with relation to units which include kilograms, meters, and seconds. So we need to relate power to these units. So there's a number of ways we can do this. One way we can look at this is in terms of force equals mass times acceleration. That means that force, work done, power is equal to force times velocity. So that gives me that power is equal to mass times acceleration times velocity. So what does that give us? That gives us 1 watt is equal to, well, I've got a kilogram there, I've got seconds minus 2 there, meters per second minus 2, and then I've got for velocity I have meters seconds minus 1. So that gives me 1 watt is equal to 1 kilogram meters squared for those two is 3 for these. So this one is okay. So the answer, the one that's not okay, is D. And look. Right. So moving on to question 14. Okay, question 14. So we're told a mass of 2.5 kilograms. It's released from rest at this point X. It slides down a ramp. Height is 3 meters and it arrives at point Y. When the mass reaches Y at the bottom of the ramp, it has this velocity. What is the average frictional force between the mass and the ramp? So this question is a question about work done. So this is about work done. And with a lot of questions, it's a matter of figuring out what approach you want to use to address the question. And sometimes it means that you might try a particular approach which doesn't work, and then you have to go back and think about, is there some other way I could tackle this problem? So work done, which is equal to energy transferred. So we're looking at the energy transferred here. If there is a frictional force between the mass and the ramp, it means that some of the energy that's transferred is transferred to thermal energy, which is then dissipated into the atmosphere. Okay, so what are the energies involved here? Well, we've got the potential energy of the object at the start, so the potential energy at X, which is equal to mgh, so that's equal to 2.5 multiplied by 9.81 multiplied by the height, which is 3. So that gives me that the original potential energy of the object was 73.6 joules. Now the kinetic energy at this point Y is given by a half mv squared. That's equal to half times 2.5 times 5 squared, 2.5, which gives me an answer of 31.3 joules. That means that I had originally 73.6, 31.3 joules of that has been transferred into kinetic energy, which means that I have the work done is 42.3 joules. This is the work done against friction. So it is that work done that transfers the 42.3 joules of gravitational potential energy is transferred into thermal energy, perhaps a bit of sound, which is then dissipated into the atmosphere. Okay, so this is what the work done is. We know that work done is equal to force times distance. That means that the force is equal to the work done divided by the distance. So we have 42.3 joules divided by the distance, which was 5 meters, which gives me the work done is equal to 8.46 newtons. So it is answer A. Now, question 15, we have there is a car. It has a force of 500 newtons on the car. It's traveling at a constant speed. The speed is equal to 72 kilometers per hour. So we should convert that into meters per second. 72 kilometers is 72,000 meters. That's in 1 hour. So we divide by 3,600 to get in 1 second. It travels 20 meters in a second. What is the work done in 5 minutes? So distance is equal to speed times time. Speed being constant, that gives me the distance is equal to 20 multiplied by 5 multiplied by 60, which gives me an answer of the distance traveled is 6,000 meters. Okay, so I've traveled 6,000 meters. Work done is equal to force times distance. So work done is equal to 500 multiplied by 6,000. So that's 5 times 6 times 1, 2, 3, 4, 5 times the power of 5. So that would give me 3 by 10 to the power of 6 joules. Answer A. Okay, so that concludes part 1 of these multiple choice questions looking at the dynamics part of the mechanics topic in A-level physics.